At first glance, this looks like a professional laser measuring tool, but inside, it's a custom built device designed completely from scratch. It projects a precision cross laser, measures angle in real time, and packs several smart features into one handheld unit. Let me show you how I built it. Instead of building another exposed electronics project, I wanted this to feel like a real handheld measuring tool. That meant everything had to fit inside a compact enclosure while still remaining easy to assemble and repair. I started by cutting PVC sheets into small panels and assembling the enclosure with superglue. PVC is inexpensive, easy to machine, and strong enough for this kind of portable device. Once the basic box was ready, I drilled all the openings for the switches, display, charging port, and laser module. For power, I used a 2500 mAh 18650 lithium battery. Since the battery voltage isn't enough to directly power the entire system, I added a TP4056 USB Type-C charging module for safe charging and a boost converter to increase the voltage from around 3.7 volts to 5.5 volts. That gives stable power to both the controller and the laser. The Arduino Nano acts as the brain of the device. It works together with the MPU6050 motion sensor to measure the angle, while the 1.3-inch display shows all the information in real time. Everything is connected as compactly as possible so it can fit neatly inside the enclosure. After testing each module individually, I started assembling everything into the case. The switches, battery, charging board, boost converter, laser module, display, and controller were installed one by one, making sure every connection stayed secure before closing the enclosure. One feature I wanted was a battery percentage display, but without adding expensive hardware. So I used just two 100 kilo ohm resistors to create a simple voltage divider. Together they cost only about 2 rupees, allowing the Arduino to monitor the battery voltage and estimate the remaining charge. With the electronics complete, the device was fully functional, but it still looked like a DIY prototype. The next challenge was making it look like a finished commercial product. I wanted this to look like a real product, not just another DIY project. Since I don't have a 3D printer, I designed custom graphics using AI and printed them as waterproof eco vinyl skins. For about 100 rupees, the plain PVC enclosure became a much more premium looking device. It's not perfect, but I'm really happy with the result. Instead of writing a single program, I divided the software into two parts. One is for calibration, and the other is the main firmware. This makes the initial setup much easier and ensures every device works with its own sensor values. The first program automatically checks the I2C addresses of both the display and the MPU6050 sensor. If the display doesn't show anything, it still prints the detected addresses through the serial monitor, making it easy to identify and correct the configuration before installing the main firmware. Once the hardware is detected, the calibration wizard begins. Using a single button, it guides you through 13 calibration positions. The center position is measured 3 separate times, while the remaining positions capture reference angles on both the light sides. Every step collects 180 samples to improve measurement accuracy. During calibration, the software also monitors sensor stability. If excessive vibration or hand movement is detected, only that particular step is repeated instead of restarting the entire process. This helps eliminate incorrect reference values and improves the final accuracy. After calibration is complete, those measured values are transferred into the main firmware. Once uploaded, the device performs a quick startup calibration automatically and is ready for normal operation within a few seconds. Now that both the hardware and software are ready, let's see how the finished device performs in real-world testing. After powering it on, the laser and display start together. Within a few seconds, the device completes its automatic calibration and is ready to use. The large angle value is shown at the center of the display, while the moving pointer provides a quick visual indication of the device's tilt. At 0 degrees, a center marker appears, and as the device moves left or right, both the pointer and direction indicators respond in real time. The top of the display shows the remaining battery percentage and the internal sensor temperature. A single button controls every function: single press to hold the current angle, double press to switch decimal precision, and long press to perform a fresh calibration whenever needed. This project combines custom hardware, software, and product design into a single handheld tool. I'd love to hear your thoughts. If you were adding one more feature, what would it be? Let me know in the comments. You'll find the complete circuit diagrams, source code, and step by step documentation in the links below. The laser module can also be mechanically adjusted to fine-tune the beam alignment and cross position, making it more suitable for different measurement and alignment tasks. Finally, here's the completed device in action under both normal lighting and complete darkness, where the cross laser becomes clearly visible. Thanks for watching, and I'll see you in the next project.